Yes, so my talk is entitled AI for Tomographic Reconstruction, and as mentioned, my name is Andrew Reeder, I'm Professor at King's College London in the UK. So the overview of my talk will be looking at introductory perspectives, what leads us to even using AI for reconstruction. I'll then cover some of the basics of deep learning. Hopefully you're familiar already, but it's useful to do that in the context of reconstruction. And then I'll be considering a number of approaches to using deep learning in image reconstruction. Just to introduce it, just do simple image-to-image mappings, not really reconstruction, but nonetheless a useful example. And then from sinograms to image, and then iterative reconstruction with deep learning. And then I'll be looking at some more recent trends in the use of AI for image reconstruction, self-supervised approaches, often not needing any training data. And then even more recently, the use of generative AI in image reconstruction. So let's get on with some introductory perspectives then. So this is the basic situation that we're dealing with. We've acquired data with a PET scanner. This is a PET MR scanner I'm showing here, patient inside the field of view, and we've got some radiotracer distribution, and we're trying to estimate some representation parameters to represent that distribution inside the patient's brain, for example. So the scanner collects data. I'll be focusing on the example of using sinogram data. Often I'll be calling that measured data vector M to denote a fully 3D set of sinograms. And then conventionally, we have some kind of reconstruction algorithm, for example, filtered back projection or ordered subsets EM, in order to reconstruct an image, and I'll be calling that a vector X most typically in this presentation, where that's just a list of numbers representing the reconstructed image. Here I'm also showing the case for MR data, but that will not be our focus today. So we'll be looking really at how we go about reconstructing an image X from measured data M. So, conventional approaches to image reconstruction. I'm using this kind of brain here to denote the kind of models that we sit and think about. We get out our pen and paper, think it through, and come up with some algorithms. These are our own models. What we do then is we consider some input sinogram. Sorry, I'm interchanging between M and Y here. So we've got a sinogram Y here. And then what we do is, using our assumed model, is that we have some series of coding steps in our algorithm. I'm, by analogy, comparing this to steps in some kind of deep network where we have hardwired the code to take this input data using our assumed model to deliver some output image. That's the kind of conventional approach to reconstruction, the assumption of a model. And we could even compare that as being some kind of simple mapping then between some input data Y here, or M, and we're mapping that across some relationship here indicated by this red line to infer what the X was. This is an inverse problem. We're trying to find the X that explains Y, but in general we put in Y and then we infer what the image was. That's the conventional approach. Now with deep learning, what we do in the most extreme form is to say, well, let's say we don't actually know what that code is, what gets us from the input sinogram to the output image. And so what we can do is use data. So again, there's an example sinogram where we run it through multiple steps. Now of a deep network, this is an example of a convolutional encoder decoder. So you can view this as a series of programming steps with trainable parameters, if you like, kind of a blank slate of coding steps where we train up what those programming steps need to be. And then we can learn by use of example data, because what we often do in supervised learning is use pairs of sinograms, a sinogram paired with an image, and then we can learn what is that inverse model, what is that mapping to get from Y to X. And according to the quality of the data, we can learn not just the inverse model, we can also learn how to compensate for noise. And so I'm trying to depict that here by showing the fact that we could have noisy data, and we're trying to map that to some underlying image X. And so to point out then, we can even get into modeling this joint probability density, and in particular then looking at what we call the posterior density. And I'll be dealing with that towards the end of today's lecture, where we're looking at generative AI, where we'll be taking multiple samples of the many possible images X that are consistent with a particular measured sinogram Y. But okay, this is still just the introductory perspective, so we won't dive into that detail just yet. So this is our conventional approach. This will be our deep learning approach. And I'm using these images here to depict the fact that we've chosen our code based on, for example, the radon transform, Poisson statistics, modeling physics, with positron range. That's what I'm using these guys here to denote. So maths, stats, and physics, contrasted with data. And we can soon recognize that these are two ends of a spectrum, where here we've got pure data to learn the code, and here we've got pure models where we're putting the code in. And the basic characterization is the following, that if we were to use some kind of data-driven mapping, then we might see very high performance in the reconstructed image. And I hope you can already see that this example image here is, one could argue, higher quality than the image I'm showing there, just to illustrate the point here. So we can have quite high performance for this case, provided when we come to, so to speak, test time, when we put a new sinogram in, provided that's from within, if you like, the distribution of the training data, the training set that we use to train up that mapping. However, the risk, of course, is poorer generalization. If we were to put in some different sinogram, then can we trust the output of the network? In contrast, then, the pure model-based approaches will generalize well outside of distribution, but in general will have lower performance. Okay, so here's the kind of out of distribution case here. Imagine if it was now some kind of image taken from outside of the brain and we've got some different sinogram. We know that these model-based approaches will generally do well, but how will that pure data-driven approach do when it's so-called out of distribution? And so what we'll be looking at today, though, once we've considered this lower case here, is the kind of balanced methodologies where we try to avoid those two extreme cases. Most people trust the top rail there, and most people are skeptical about the bottom rail there. But what I'm going to emphasize, of course, is that we don't have to take such extreme options. Okay, so here are example methodologies that fit within that kind of framework. The top rail there, we're dealing with, say, filtered back projection, maximum likelihood expectation maximization, maximum a posteriori reconstruction. And on the bottom rail here, we've got the kind of pure deep learning approaches, heavily relying on training data. In MR, there was AutoMap. In PET, there's Deep PET, which I'll touch on later. And then I'll be talking about these middle range methods where we're trying to draw some compromise between those two extremes. Okay, and one other point to note is that, of course, in this top rail, there is high interpretability, and at the bottom rail here, there can be harder ability to interpret what the network is doing. So to briefly visit then those model-based methods, we've got filtered back projection there, we've got MLEM reconstruction there, and then we've got MLEM with PSF modeling, showing the improvement in modeling of the statistics and then improving modeling of the physics. This is just like a review of what we did for the model-based reconstruction methods. And then if we were to even have high-quality images like that, what typically happens is that we then go to shorter scan times, and then we're in the need of trying to improve image quality again. So if there were, this is a different scan here, but if we only had 5 minutes of data, we could have a lot of noise. There's a need to regularize. But then you can lose detail, and so often we can use MR guidance information and get some kind of improvement in the reconstructed image quality. So this slide is really trying to capture where non-deep learning based reconstruction had got to, for example, in PET imaging. So MR guided, regularized PET reconstruction. But there are issues, and so if we just look at MLEM, if we're looking at high count data, we might have a high quality image. But of course, as we reduce scan time or reduce injected dose, then we could end up with the classic overfitting to noise in the OSCM algorithm, and that's what I'm showing here. If we were to go to conventional regularized methods, MapEM, with a simple quadratic objective, then we're at risk of over smoothing that low count data, and so we get a loss of detail. And then if we were to build in MR information, the big risk there is that we're making assumptions about how to use that MR information. And so that's where I'm showing an example here of this is using the Bauscher method for looking at how to control the smoothing in the PET reconstruction. And then we're at risk, hopefully you can see that here, of getting misguided information here where we've smoothed according to the patterns in the MR and that is now an erroneous reconstruction compared to what that structure should look like in that region of the brain. So this begins then to motivate the case for use of deep learning in reconstruction, because as we've just seen, noisy low resolution data will often give noisy images, and if you try and model resolution in reconstruction, you can get so-called Gibbs ringing like artifacts. If we try and compensate for noise, our methods can be too simple, the loss of detail with a quadratic prior, or all kinds of assumptions which don't hold up well, total variation, relative difference prior. Relatively safe, but not as exciting as some of the MR-guided methods. But then the MR-guided methods can be too imposing and get things wrong. So conventionally then, we're assuming we know what the system model is, we're assuming we know the data noise distribution, and we're even making assumptions about how we regularize. So this is where deep learning comes in to say, well, we can use real data examples to learn what the imaging and noise model should be in their so-called inverse. And then in particular, and this is where it's often mainly used, is we can use deep learning to embed knowledge of what the ground truth images would look like. In other words, learning the probability density function for high quality images and then building that in to our reconstruction framework. So to understand that concept, it's really important to understand the concept of manifolds. So here I'm imagining these images are just composed of 3 pixels, if you can imagine that. Then any given image, if it had only 3 pixels, would be a point in a 3-dimensional vector space. So pixel value x1, x2, x3. Then we could have a so-called manifold, a kind of a, if you like, some region of that 3D space. Of course, this would actually be maybe a 10 megapixel image, in which case that'd be a 10 million dimensional vector space. We've got a so-called manifold, for example, of natural images, where we could think about some probability value for each of the possible positions in that high dimensional vector space. So we'd have a manifold for natural images, a manifold for MR images, and then another manifold, some probability density function in that high dimensional vector space for, say, high quality FDG PET images. And then what we're trying to do, excuse me, is take our noisy reconstruction, for example, and effectively try and get that to be somewhere on that high quality manifold. So that's just a very introductory concept of what is often being done in deep learning based reconstruction. Okay, so some basics of deep learning then for reconstruction. Conventionally, here's a ground truth image, which is normally ignored, of course, in conventional reconstruction. We've got some ground truth image for which we collect some measured data. And then what we're doing conventionally in reconstruction is taking some guess of what that true activity distribution is, and we apply some forward model, some system matrix to predict, to actually model the mean of the measured data. And then what we do is compare the measured data to our forward model of the mean. And then we use an objective function to compare between our model and the measured data. And that could be, for example, the Poisson log likelihood, or an MR, it could be a least squares objective function. And then we're trying to find some image X, which minimizes the discrepancy, the distance between the forward model and the measured data. And then we use some optimization algorithm to update X such that it better agrees with the data. Well-known methods for this are MLEM or OSEM. We'll visit this again later on. Or if we're into a direct least squares solution, then we could assume a Gaussian noise model and do some direct least squares inverse. Although in practice, even in MR, there'd be often iterative conjugate gradient based methods. So that's conventional. And as I'm just kind of repeating a bit here, as pointed out, the problem is that X here is being fitted to noisy data. In which case we need to regularize this level of agreement by using some penalty function, some regularization. But as mentioned, we don't really know what that penalty should be, how strong the hyperparameter should be to control the level of regularization. And again, we're assuming that we know that system matrix, and we're assuming we know what's the best kind of noise distribution to model that measured data. Now, with deep learning, as you're probably already realizing, deep learning in its purest form is really just doing a very, in supervised context, it's just doing a very high dimensional regression. So if we were mainly leaning on training data then, what we're saying is we'd have pairs of data. I'm just showing example sinograms paired with ground truth images here. And a key point to notice is that on this axis here, we would have ground truth or high quality reference data. So high quality reference data could be corresponding to a very high count acquisition, or if you've got simulation available, it could be the ground truth image. And then you're linking these ground truth images or high quality references with noisy measured sinograms. And then the goal then is to find this mapping that takes you from the noisy sinograms to the high quality references. And so we're calling this supervised learning. Try and find some mapping. So this is going to be a deep network F, parameterized by some vector of trainable parameters theta hat, where theta hat is the optimized set of parameters for that deep network F, such that when you operate on some measured data M, you get hopefully some estimate of the underlying ground truth image or object representation. And then, so this is depicted here, we're trying to find the parameters theta for the deep network F, such that when you operate on M, you match the ground truth T. And we use some distance measure, some discrepancy measure between the two, which is the loss function. So often this would be a mean square error, L2, or it could be a mean absolute error, L1. And then the point being that if we've trained up that mapping, if we're within distribution, the idea is that we would have some new sinogram and be able to do the inferring of the underlying ground truth by using this pre-trained supervised deep network to then, if you like, very rapidly reconstruct a high quality image. So let's look at this in the simple image to image case then. So I'm going to rapidly go through a few examples here, single kernel, CNN, and then a UNet to see the image to image mapping in action. So this is just a very introductory example. Imagine our reconstruction was in fact just a restoration task of denoising. They would be putting noisy images here into this mapping, and would be trying to find the denoised reconstructions by supervised learning. So how would that look? Well, that would just be, for example, a convolution matrix. If we would just train up one kernel, we could say take some noisy image M and then train up just one single convolution kernel, just to show how simple this can be. And in fact, that's a very key benefit of using convolution, is that we can get away with one convolution kernel composed of 3 by 3 elements, in other words, 9 trainable parameters, to actually do an entire image to image mapping rather than learn the entirety of this huge matrix F. So what would that look like? We'd vectorize our noisy input image here, and that's just a vector M. We would then have this circulant matrix where we just have the convolution kernel just duplicated along the rows or columns of the matrix F, and then we would be getting some output from that convolution. And all we need to do then is train up the values. 9 values will actually be able to, just by deep learning, even with one single training example, we'll be able to train up a best kernel for denoising. So I've got a simple example of that. Hopefully this is going to run. Let's see if this is showing what's going on. Here I'm using some input noisy data, and then I'm training up in real time one single convolution kernel here to try and match this high quality target. And you can see that as this input is getting noisier and noisier, so my single kernel is getting broader and broader in order to, when this is convolved with this, to best match that target. And you can see that this one single kernel is struggling a lot when I get very noisy. And as I get to less noisy, then you can see that this kernel is getting narrower and narrower. And so this is like showing a real-time adaptation of learning of one single kernel to best match the target. And in fact, here I think I'm now cheating and actually using a CNN and showing that if I do many layers of many convolutional layers of many channels, then in fact I can very rapidly get a much higher quality output compared to using one single convolution kernel. But the point to realize here is that even one single convolution kernel is actually a very powerful mapping. So this just rapidly illustrates that. There's the noisy input. Forgive the changes of notation here, if you'll allow me to call that a vector X, running it through just one convolutional kernel of 9 parameters to get some noisy output if this is a delta function, and then I'm training it to match this target, this labeled data, and I'm going to be learning what are the values in that convolution kernel in order to get that input to best match that target. And we do that, for example, here with just one training pair only, and then we define some loss function to look at the difference between my output and my target. So we just look at the values in y and the values in t, and then we square the difference in those values, sum them all up, and that's our mean square error loss function. We can use some kind of optimizer, a gradient descent based approach, Adam optimizer, whatever your favorite method is. And then that shows that we can learn 9 parameters indeed to just do the best we can to smooth that to best match the target. So hopefully this conveys the simplicity of what's going on with training and mapping to try and match a target. Flexible as it is, you can also learn how to de-blur an input image. Here's a blurry image, there's the sharp target, and now just by using a 5x5 kernel, in fact, I think here we just did a step search, grid search for all the different values here. Very easy to learn a 25 parameter 5x5 kernel to sharpen up that input such that it matches the high quality target. So these then are the essential components. In general, we need training data, and I'd really like to emphasize we can deal with cases of no training data, as we'll be touching on later on, through to tens of examples to tens of thousands of examples. And that often depends on the complexity of your mapping, the inductive prior of your network, how big it is, and so on. But there's a lot that can be done with no training data at all. Then we need a design of that mapping. I've been showing some simple linear mappings and some convolution-based mappings. That's the so-called inductive prior of the mapping from the input to the output. And so we can use CNNs, transformers, whatever your favorite network might be. And then we need some loss function to check whether our mapping is doing its job. Mean square error, mean absolute error, perceptual loss, adversarial loss. And then often we use holdout validation data in order to check how well our mapping is doing on separate data. For example, to train up the number of so-called hyperparameters. That might be the number of epochs to train for, the parameters in the optimizer, such as the learning rate, even ideally to choose the inductive prior as well. In other words, choose the architecture as well. We can use validation loss to explore that. And then, of course, a choice of optimizer. So even image to image, we've got some very nice results. These are results from Georg Schramm, published back in 2021, where he used just a convolutional neural network to take a vanilla OSCM reconstructed image and get it to deliver what normally takes quite a while to process, which is a MapEM, MR-guided MapEM reconstruction. So just by training up pairs of data, so OSCM with its MR, T1 weighted MR, then they do the slow reconstruction to get the target, and then they just train up this large convolutional neural network to go from the low quality OSCM to the high quality MapEM. And so there, rather than the simple examples I've been going through earlier of just 9 or 25 parameters, here with a CNN you can often be dealing with 170,000, even millions of trainable parameters. Here they only had 26 training data sets. I'd have to look at exactly how many subjects were involved in that, looking at different tracers, different scanners, and using a simple mean square error loss. And also importantly, they did a residual learning, whereby they don't learn how to map from here directly to there, rather they learn what is the difference. In other words, what do you need to add to this in order to get to that? And so this network focuses on learning the difference rather than the entire mapping. And why do they do that? Well, for getting MapEM reconstructions, they can get them in far quicker timeframes. So that's their motivation in this particular case. At test time, using out of distribution data, so a different radio tracer, very impressively, they got this kind of, so OSCM input, MR input, and getting a predicted MapEM reconstruction compared to the actual MapEM. They got some very nice results indeed. Just also one final rapid example on the image-to-image mappings before we move on. This is an increasingly well-known approach. This is an old version of it from 2021, so-called FastPet, where they back-project time-of-flight-based PET data to get a so-called histo-image. And then all they do is train up a UNet in order to map from the time-of-flight-based back-projection to maybe not so exciting, but just to the OSCM reconstruction. Obviously, they have many options for what they use for the label here, the target. but they chose regular OSEM. And again, this motivation is that they get this massive speed up, and again, only dealing with maybe 20 million trainable parameters, which may sound like a lot of trainable parameters, but of course, as I'll point out later on, if you were to actually look at the number of parameters in even just a matrix going from an image to image, it would normally be many, many more parameters than that. So 20 million is actually already making a lot of assumptions about the kind of mapping from one image to another. Okay, so let's move on then to going from sinograms to images. So perhaps the most famous example of this for PET reconstruction is the so-called deep PET architecture. Well, what they do is by using, I think, hundreds of thousands of training pairs, they end up with the following network where you can put in a 2D sinogram. So here I'm showing the dimensions of the sinogram they used. So this is like a point in a 77,000 dimensional vector space. They run this through downsampling-based convolutional layers, effectively to encode that into what we call a latent space representation. Now, I find there are a lot of misunderstandings here, possibly even from myself years back as well, that this latent space, this bottleneck, isn't necessarily, as in a conventional autoencoder, isn't necessarily a low-dimensional representation. You'll notice here, if you do the calculations, actually we're going to a much higher dimensional abstract representation of that sinogram data. So this is, if you like, encoding that information into some high dimensional latent space, some kind of explanatory underlying values, which can then be decoded with via synthesis, a decoder, a generator, to then re-express that common information now in the form of an image. And here, just a 128 by 128 image, 16,000 dimensions in a vector space. So a convolutional encoder decoder, they use 200,000 training data pairs to learn now a 60 million parameter mapping, CED, using mean square error loss. And again, as I've been touching on before, if you were to compare that to a simple linear mapping, imagine you try to train up the entirety of, say, a filtered back projection entire matrix going from one to the other, you'd actually need more than 1 billion parameters to do that mapping. So this convolutional encoder decoder, even though it's going to a higher dimensional representation here, is still very parameter efficient. And that's why maybe you can get away with just 200,000 training pairs there. So their results are, really very instructive. If you look at they use simulated data. I think it was Monte Carlo. So they get the high quality ground truth and they get the simulated data. They've compared their deep PET reconstruction with filter back projection and OSEM, and you can see very convincing improvements in image quality. This is strikingly similar to the ground truth, far outperforming OSEM and filter back projection. So no surprises if you compare SSIM, structural similarity, between their deep PET reconstruction, they are indeed outperforming the conventional methods. But that's because they're within distribution, within the training set that was used. If you start to go to real data out of distribution, then the results they report are perhaps a little bit disappointing. There's the filter back projection, OSEM, and then if they used this network trained on simulated data, I'm sure you'd agree, their outside distribution case is not particularly convincing. I'm not even sure I can see a very good chordate putamen in the middle of that brain. So they get improvements in image quality generally, and again, massive acceleration compared to OSEM. There was a variant on this, just to briefly touch on this. So Zhanli Hu et al. A couple of years later took on that same convolutional encoder decoder architecture, used the same mean square error loss function to map from a sinogram to an image. And if you like, is a generator network. I prefer to view the decoder as the generator network. But what they did was then add on a discriminator. This is of GAN fame, generative adversarial networks, where effectively you're training a discriminator network to try and identify whether the images that are generated here actually look like real images from your training set, or indeed synthetic ones. And so this is just a famous alternating min-max so-called game that goes on, where the generator is trying to generate images that will fool the discriminator, and the discriminator is trying to catch out the generator by saying, yeah, I can recognize that that's one that you created rather than one from the training set. I won't go into this in any great detail because we're finding GANs are really beginning to get out of fashion now. They're very finicky with their training. And as I'll be presenting much later on today, diffusion-based methods, generative AI-based methods are now really taking off. But just to complete the picture here, with this greater generalization of the deep pet method, they used mean square error loss, they used this adversarial loss, and then they used so-called perceptual loss, which is quite an important concept. That's where you take some image and then you could use some kind of convolutional encoder, some kind of so-called convolutional backbone, deep network backbone. Here it's the VGG network that's pre-trained, for example, on ImageNet data, whatever it might have been. So you can take some image and then using multiple convolutional layers, encode it to some latent representation. And then what you can do is compare between reconstructed images and the true ground truth just in terms of the latent representation rather than the pixel level comparison. So they used this perceptual loss, comparing the encoded version of an image, the pixel level mean square error loss, and then also the adversarial loss. And to show just some of their quick results here, you can see that their method with those two extra loss terms rather than just mean square error, if you were to look there compared to the so-called ground truth over the left here, you can see that they're doing a bit better than the simple mean square error based deep pet methodology. And again, definitely outperforming EM with post smoothing. So this is actually our Quadra PET scanner at St Thomas's Hospital, King's College London. Just to show quickly in a moment some results from Bern in Switzerland, where they have had the deep pet method for their Quadra data. And so it's very similar to what we've seen before, except they're wanting this to work, of course, for 3D data. And so what they do is so-called single slice rebinning, which is a very crude mashing of the data in the axial angles that you just collapse it all to a set of direct plane sinograms. And here's one of them here. Again, it's adopting the same convolutional encoder decoder architecture inspired by Hagstrom's deep pet. And they also use that perceptual loss that I've just spoken about earlier as well. So they can use mean square error loss to check the reconstruction here compared to some ground truth. Now, their ground truth is just a conventional reconstruction with all the data corrections built in. So maybe that's the advantage here, is that this network then can learn how to handle the data corrections and deliver very fast reconstructions to try and match the conventional reconstruction using mean square error loss as well as the perceptual based loss. And hopefully also it correctly undoes the shocking mashing effect of single slice rebinning. But as we'll see with their results, all published, I'd say still a work in progress. This is the vendor-based reconstruction of a couple of different example data sets. This is the Hagstrom deep pet method with just that mean square error loss. Pretty shockingly erroneous, I'd have to say, in some places here. And then with their extended version here, you can see they are getting closer to the vendor reconstruction, but and they're better than deep pet, but they're still not quite there yet. So that's a work in progress. The appeal being just a lightning fast reconstruction with all the data corrections built in. That would be the appeal there. Okay, so let's try and summarize roughly where we've got to so far then. These are the model-based reconstruction methods. We could look at them in terms of any deep learning, any so-called handcrafted components. Those are the bits that are just based on our knowledge, our thinking about the reconstruction problem. And so model-based methods don't have any deep learning. They use our knowledge of physics, stats, maths, and so on. We know that they're good at generalization outside distribution because they've not relied on training data. They can do 3D reconstruction, no training data, no network. They can be slow to fast reconstruction, filter back projection, or map-EM, takes a long time. Image quality, not bad. They're simple, established, trusted, and seemingly reliable. Now, we've just been looking just now at full-on deep learning-based reconstructions from Sinogram to image, and there they've gone all the way to the other extreme, where the deep learn parts of the model, yep, let's deep learn all of it. So that's the all. Let's basically largely forget about our knowledge of physics, stats, and maths, and so on. Generalization, though, can be challenging, as we've seen in some examples, and even true 3D reconstruction could be challenging. We've seen that last example, the single slice rebinning, turned it into a 2D reconstruction. Very data hungry, more than 10,000 example pairs of data. Relatively large networks, although remembering they're still smaller than what it might be with a naive matrix mapping. But they can be lightning fast. And if you're within distribution, you can get excellent image quality, so fast and high quality if you're within the training set distribution at test time. So you can see there we've got two extreme cases. So that's obviously appealing back to the earlier part of my talk where I was showing those two rails of model-based reconstruction and then pure AI-based reconstruction. And now we're going to look at the more frequently visited middle ground, which is to use a combination of our knowledge of physics and maths and stats with deep learning. So we're going to embed deep learning then into iterative image reconstruction.